Well, good morning. It's a pleasure for me to be back in Oxford. I've been here many times, but actually not for some time. I think 10 years, probably 10 or 12 years was the last time. So today I'd like to talk about elections, voting. One of my non-academic endeavors is to try to get voting reform accomplished, particularly in the U.S. One issue that comes up with voting systems is strategic voting. By strategic voting, I mean a voter not voting according to his or her true preferences. If I prefer candidate A to candidate B, I might nevertheless assert that I prefer B to A in order to stop candidate C, who I despise, from winning. And that sort of phenomenon, strategic voting, comes up a lot in practice. There are very famous historical episodes where strategic voting took place. But I think there are at least two reasons why voting rules which are vulnerable to strategic voting are to be avoided. One is simply the idea that if we go through a voting rule's properties, the nice axioms that it satisfies, and we decide that we're going to choose this voting rule because it has these nice axioms. If it turns out that voters are not actually voting according to their true preferences anyway, the nice properties that we thought we had might no longer hold. So that's one reason why strategic voting is not such a good idea. But I think an even more important reason is that if a voting rule is vulnerable to strategic voting, that makes it much harder for voters. If I'm a conscientious voter, I need to do my homework on the candidates. I have to read up on their positions, perhaps listen to their debates, et cetera, et cetera. That's a fair amount of investment of time and energy. If on top of that I have to guess how other voters are going to vote, if I have to invest time and energy in predicting what other voters are going to do so that I can react against it in a strategic way, well, then my decision problem is several orders of magnitude more complicated. So one good reason for trying to avoid strategic voting is that it makes life easier for voters. They just vote according to how they truly feel about the candidates. But unfortunately, we run immediately into the Gibbard-Satterthwaite theorem, which probably many of you, most of you, have heard of, which says that at least when preferences are completely unrestricted, there's essentially no voting rule except for rather unattractive ones like dictatorships, which are strategy resistant, strategy proof. Now, that's unfortunate, but there's a sense in which I would argue it's too negative, because in reality, preferences aren't anything. In most settings, there is some structure to the preferences, and we might be able to exploit that structure to avoid the Gibbard-Satterthwaite result. And in particular, a famous example of that was Duncan Black, who argued many years ago that in political elections, perhaps preferences are single-peaked. And let me remind you of what single peak preferences are. The idea is that the candidates are arrayed along a line, say from left to right or liberal to conservative, using the American terms for liberal and conservative. Each voter has a favorite candidate, and as we move away from that favorite candidate, the voter's utility goes down. So if we graph a voter's utility, along the horizontal axis we have the candidates, along the vertical axis we have the utility. If we graph utility, it has a single peak. The peak is at the candidate, at the voter's favorite candidate. That seems a plausible assumption. I'm going to talk a bit at the ends. There is actually an empirical part of this paper which looks into the question to what extent are real-life political preferences single-peaked. I will partially give that away now, which is to say that, of course, they're not completely single-peaked, but they will be close enough so that the theory of this paper still applies. And I hope there'll be some time to talk about that. Anyway, that's single peak preferences, and what Black showed is that a very attractive voting rule, perhaps the one we first learn about when we learn voting theory, majority rule, or Condorcet voting, works very nicely on single peak preferences. Majority rule is the voting rule where voters rank candidates in order of preference. And given the rankings, we elect the candidates who would beat each other candidate in a pairwise comparison. So candidate X beats candidate Y if more people rank X above Y than Y above X. A Condorcet winner is simply the candidate who beats all of the other candidates in such pairwise comparisons. Here's an example. There are three candidates, red, purple, and blue, and I've indicated the proportions of the population who have each ranking. So 46% have red as their first choice, then purple, then blue. In this example, the Condorcet winner is purple, even though, as you see, only 25% of voters rank purple first. Why am I not advancing this?
You have to point it to the computer.
Oh, I have to point it to the computer, okay. So purple beats red because these people and these people and these people all prefer purple to red, and that adds up to 54%. And purple beats blue because everybody but this group prefers purple to blue, and that's 71%. So the Condorcet winner is very clearly purple in this example. Now, Condorcet voting is not infallible. Condorcet himself showed that it may fail. There may not be a Condorcet winner. The famous example was something like this. three groups of voters, three candidates, X, Y, and Z, three groups of voters, X beats Y. These voters prefer X to Y, and these do too. That's 66%. Z beats X. These voters prefer Z to X. These voters prefer Z to X. That's 67%. But Y beats Z. These voters prefer Y to Z, and these do too. That's also 67%. So no Condorcet winner in this example. But this example violates single peakness. As Black showed, if we do have single peakness, then a Condorcet winner must exist. Actually, the argument is very simple. Let me remind you of it. Let's look at the favorite candidates for each voter. And now let's look at the median candidate. That's the candidate for which more than 50% of voters have their peak at that point or to the right of the median, and more than 50% have their peak at the median or to the left. Well, then notice that if we compared the median candidate with some candidate to her left, all the voters on the right, and all of the voters who like the median candidate best, will prefer the median candidate to the candidate on the left. And that is, by definition, a majority. So the median beats the candidate on the left. But symmetrically, the median candidate also beats the candidate, any candidate on the right. The median candidate is a Condorcet winner. Let's go a step farther and ask, well, is Condorcet voting invulnerable to strategic voting? And there's a particular sense, a limited sense, in which it's been known for a very long time that it is immune from a certain kind of strategic voting. This is an argument developed by Dummett and Farquharson. Michael Dummett was here at Oxford. Would some voter or some coalition of voters gain by voting strategically and creating a false Condorcet winner? So we're supposing that the actual preferences, the true preferences, are single-peaked. Would some coalition gain by voting in some strategic way which causes some other candidate to be the Condorcet winner? Let's suppose that X is the true Condorcet winner, but the manipulation causes Y to win. And what Dummett and Farquharson noticed is that if you were part of a coalition trying to get candidate Y to win, of course you would want to prefer Y to X, otherwise you wouldn't be a member of the coalition. But if you preferred Y to X, you already preferred Y to X in the true profile. And so your manipulation couldn't make Y the false Condorcet winner. So that is the sense in which Condorcet voting is immune to strategic voting. It doesn't give coalitions the incentive to create a false Condorcet winner. But the problem with this argument is that it neglects what happens if a coalition perhaps doesn't create a false Condorcet winner, but creates a Condorcet cycle, as in Condorcet's example a few slides past. That is, manipulates in a way so that there's no Condorcet winner. Let's take a look at that. This is the same profile I looked at a few minutes ago, where purple is the Condorcet winner. Suppose that it's easy to check that these preferences are single-peaked. We have red, purple, and blue along the spectrum. Purple is the candidate in the middle. So what if the red voters manipulate and pretend that their ranking is red, blue, purple? Well, we get this profile instead. Now there's no Condorcet winner. Red beats blue, blue beats purple, purple beats red, if I've done the arithmetic correctly. So we have no Condorcet winner. What do we do then? Well, there's a large literature on what to do if there's no Condorcet winner. There's some other Oxford people who have contributed to that literature, including Lewis Carroll and Peyton Young. In fact, I will be mentioning both of them on the next slide. But for the moment, let me look at another proposal by Black, Duncan Black, which is to elect the Condorcet winner if there is one, but otherwise elect the Borda winner. Just to remind you what the Borda winner is, if there are 3 candidates, voters rank the candidates. Every time a candidate is ranked first, she gets 3 points. Every time she's ranked second, she gets 2 points. Every time she's ranked third, she gets 1 point. We just add up the points, and the winner is the candidate with the most points. So in this example, red is the Borda winner. You can, again, I think I've done the arithmetic right. Red has the most Borda points. But that's, if we use Black's method, then these voters, these red voters, are going to want to manipulate. By the way, this also shows that, I mean, we already knew this, but this also shows that the Borda count is manipulable. I happen to like the Borda count a lot. So does Peyton. Peyton was perhaps its first axiomatic advocate for Borda. I've even gone so far to say that if Arrow had done his impossibility theorem in the right way, he would have come up with Borda, not an impossibility theorem. But anyway, Borda is manipulable, and so although I think it's quite appropriate for some settings, Borda said, oh, but my voting system, Borda knew that his voting system was manipulable. He said, but it was intended for honest men. Of course, the members of the Econometric Society are all honest, and so it's fine to use the Borda count as we do for council elections. I have no objection to that. But political elections, are another matter, because we have a lot of data on manipulations in political elections. So then the question arises, well, Black's method is manipulable. We can't use that. What about one of the many others that have been proposed? Copeland's method, Kemeny-Young, this is Peyton-Young, Minimax, Nansen, Dodgson is Lewis Carroll. There are literally dozens of them. They are all manipulable. So the question is, well, might there be something else that's not manipulable? Well, I wouldn't be dragging you out this early in the morning if the answer were no. Fortunately, there is a method that is non-manipulable. And furthermore, it's unique, as I hope there'll be some time to show. And to motivate this method, let's look at this profile here. Notice that there's a sense in which there is more diversity among supporters of purple than for either red or blue, in the sense that purple voters might put red second, or they might put blue second, whereas the voters for the extreme candidate, the supporters for the extreme candidate, have their preferences pinned down. Now, I'm doing this for the case of 3 candidates, but actually the same principles apply no matter how many candidates there are. We expect more diversity in the middle than we do at the ends. And let's try to exploit that fact in our voting rule. So what I propose to do is, for each candidate, we will calculate that candidate's diversity score. The candidate will get 1 point for each different ranking in which she is placed first. So that means that in this example, purple has a diversity score of 2 because both of these rankings appear. 2 different rankings appear where purple is at the top, but red and blue have diversity scores of 1.
So this is without regard to the population frequencies of the rankings.
Yes, yes, that's right. So it's different from other rules that have been used in the case where there's not an immediate clear-cut winner. So here is how we're going to do the election. Voters are going to rank the candidates. And if there's some candidate who, according to the rankings, is the Condorcet winner, then that's it. She's elected. If not, then we look for the candidate who has the lowest diversity score. There could be a tie. If there's a tie, then we break the tie by dropping the candidate who has the fewest first-place votes. So,
this is not weighted with how many?
I'm sorry?
This is not weighted with how many? I mean, because here both red and blue are the lowest.
Yes.
Red has a more support.
That's right. So so in this example, blue will be eliminated, exactly. And then we just iterate this process until some candidate is a Condorcet winner among the remaining candidates. And because there are only a finite number of candidates, the process will come to an end. So in the example, well, we have an outright Condorcet winner, purple, so we don't have to worry about what happens if there's no Condorcet winner. But suppose that we look at a manipulation similar to the one that I was discussing a few minutes ago, where the red voters, or at least some of the red voters, pretend to have a different ranking in order to perhaps change the winner from purple to red. So let's suppose that 26% of the red supporters submit this false ranking, red, blue, purple. And you can check that as in the previous analysis, there's no Condorcet winner. And furthermore, by making this manipulation, red has now had his diversity score raised to 2. So he now ties purple. Now there's no Condorcet winner, so what do? We drop blue, because blue has the lowest diversity score of 1. So we drop blue, and now it's a contest between red and purple, but purple still wins, because all of these voters prefer purple to red. So the problem for the red manipulators is that they can't manipulate in a way that gets red preferred to purple by a majority. And so, at least in this example, manipulation does not pay. Okay, but turns out it never pays if we use these voting rules, at least under the following assumptions. One assumption is that voters' true preferences should be single-peaked. That's what we've been assuming all along. Second, that all possible single-peak preferences do appear, so we don't have holes where no one has a particular single-peak ranking. We'll call that the fullness assumption. And then third, we're actually not going to allow for all possible manipulations by a coalition of voters. By the way, the reason I'm talking about coalitions of voters rather than individual voters is because in a real political election with millions of voters, no single voter is going to make a difference, but a coalition might make a difference. So it's natural to look at coalitions. Yeah.
So 2 means not only that every possible candidate is a possible peak, but also that outside the peaks you have all possible rankings, left and right of the peak. Is that what it means?
All possible single-peaked rankings.
Yeah,
So,
but it means
so in this example, there's only, if red is at the top, the purple and blue are the only possible. Only red, purple, blue is possible according to single peakness.
Yeah, but I mean, but to the left and the right of your peak, you can rank the outside candidates differently, not just according to the peaks.
There are all the possibilities.
There's a lot of possibilities. There's a lot of possibilities left.
Oh yes, sure. With 3 candidates, there aren't that many. There are 4 possibilities, but with more than 3, that the possibilities go up quickly. Sure. And then the third assumption is that not all manipulations are being perpetrated by a coalition. A coalition doesn't necessarily just have to manipulate in one direction. It could have some of its voters vote one way and other voters vote another way and a third group vote a third way. But what we're going to do is we're going to restrict coalitions, if they are manipulating, not to manipulate on both sides of the Condorcet winner. And I think there are several good reasons for that. First, that kind of manipulation would be, in practice, extremely difficult to undertake. Hard enough to get your supporters to vote for your candidate. But if on top of that you have to have some of them vote for other candidates, that's complicated. And furthermore, it's dangerous. If you have red voters who are submitting blue as their first choice, well, they might well end up electing blue, which is the worst possible outcome for them, unless they're very sure of what the true voting profile looks like. So at least under these assumptions, the election rule I've shown you is non-manipulable. And so this is not quite strategy-proofness, as I said, because we're assuming that we're not claiming that truthful voting is going to be a dominant strategy if the other players do not have single peak preferences, and we're also limiting the way that coalitions are manipulating. Since this is a Nash conference, I have to make a connection with Nash equilibrium. There's a sense in which what we're asking for is a strong Nash equilibrium. That is, no coalition. A strong Nash equilibrium is one where no coalition benefits from deviating unilaterally, and we get that here, except that we're not allowing for all possible manipulations. Now I'm running out of time, right?
2 minutes.
2 minutes. So let me just mention two other results that go along with this one, which is, first of all, uniqueness. I showed you a voting rule which works. It's the only one that works. Or anything else that works has to be formally equivalent to this. That's not terribly hard to show. And then going a step beyond that, well, we might ask, what if we don't concentrate on Condorcet rules? Is there some other voting rule which might also be strategy resistant when voters' preferences are single peaked? And the answer is there isn't, as long as we require those voting rules to be anonymous, meaning that all voters count equally, and neutral, which means that all candidates are treated symmetrically. So we get that uniqueness result as well. But let me spend a minute. I'm going to skip the proof of theorem 2 unless someone wants to see that later. What is the sense in which single peakness is actually a good assumption? We actually now have quite a lot of data on that question from American elections. There are two states in the US, state of Maine and the state of Alaska, which went over to ranking elections. They're called ranked choice vote elections some years ago. Maine did so in 2018. Alaska did so in 2022. And so we actually now have several hundred elections to look at this question. And we have the data from those elections. We have all of the rankings. So we can check whether rankings really truly are single-peaked or not. Now, there are two senses in which literal single-peakness would be too much to ask for. Many voters don't even rank all the candidates. A fair number just vote for their favorite candidates. That's a violation of single-peakness, but we can do pretty well with incomplete rankings as long as we attribute the incompleteness to indifference. So if I just vote for A and I don't say anything about B and C, implicitly I'm saying I like A more than B and C, and I'm treating B and C as though they're indifferent. And our theoretical results still work pretty well under those circumstances. Now, there are some outright violations of single-peakness where someone voting for a left-wing candidate will put the right-wing candidate second. But those turn out to be relatively rare. There is typically a fairly low threshold, say 4%, where we don't see more than 4% of voters expressing a non-single-peak preference. And that means that if we modify our voting rules so that a candidate doesn't get a diversity point unless the fraction of the population expressing a particular ranking is over the threshold, then everything I've said goes through. And 4% turns out to be the magic number, at least for the elections we have so far. If we use that rule, then one, Condorcet winners always exist in all the elections that have taken place. And furthermore, all of those Condorcet, all of those elections using the election rule that I'm proposing would be non-manipulable. Now, there's a problem with the data, and this will be the last thing I say because Vince is staring at me. There's a problem with that data, which is that the elections were not actually Condorcet elections. They were what are called ranked choice vote elections, in which voters do rank the candidates, but we don't necessarily elect the Condorcet winner. I won't describe how RCV actually works, but so you might worry that if we change the rules and did Condorcet voting instead, perhaps the rankings would change. There are some fairly straightforward theoretical arguments which suggest that they probably would not change very much. Certainly they wouldn't change at all if voters were voting truthfully. Okay, I think this is a good place for me to stop.
We have time for one question. I'll let your questioner. Yes, sorry.
There's a question right there.
Thank you for giving me the unique opportunity. Very nice talk. One sort of maybe more social question. New York City just had a ranked choice voting in a primaries.
Right.
And from what I understand, ranked choice voting is really hard on the population. They have trouble understanding it. They have trouble researching enough candidates to have enough options. New York City had a lot of options. You commented that ranked choice voting, if they choose it truthfully, is simpler, but I'm not so sure I buy that. Do you have any comment on that?
Okay, so it is true that voters find elections where they have to rank candidates more complicated than ordinary plurality rule, where voters just vote for their favorite candidate at first. Now, New York has had ranked choice voting in just 2 elections so far, but the evidence suggests from Maine, where they've now used it 4 times, 2018, 2020, 2022, 2024, that by now voters are much happier with it. So yes, it takes some getting used to, but voters do get used to it. And more important, in both New York and Maine, and also Alaska, where a ranking system was voted in, it wasn't voted in by the politicians. This wasn't a law that was passed over the objections of the public. In all 3 cases, it was by voter referendum. And so even from the start, a majority of voters, or at least a majority of voters who bothered to vote, preferred to have ranking rather than old-fashioned plurality rule. In Australia, where they've been using ranked choice voting for their lower house of parliament for over 100 years, ranking is second nature to those voters.
Thank you. Let's move on.
Okay. Okay.